We are continuing with Rao Bhim section 7.6. Theorem 7.6.4. It gives a quick way to manufacture new orthogonal matrices from given orthogonal matrices or unitary matrices. If A and B are unitary, then their product is again unitary. A star, A inverse, A transpose, A bar are all unitary matrices. The proofs are absolutely straightforward, simply by using the definition in the form A star A equal to identity or A transpose A equal to identity in case of orthogonal matrices. A somewhat less trivial setup is this. You have a matrix A and you put another matrix B and you make them in this way. So block diagonal matrix. Then this block diagonal matrix must also be unitary, simply because if you take star of this, you will get A star, B star, 0, 0. So this 0 has basically come here and this 0 has gone there. Now when you multiply, because of property of diagonal matrices or block diagonal matrices, these two things get multiplied and these two things get multiplied. The zeros contribute only zeros. So you will get identity, identity, and 0, 0, which is just a big identity matrix. Theorem 7.6.5, if A is a unitary matrix, then its determinant, which in general is a complex number, has modulus equal to 1. In other words, its modulus must lie on the circumference here of the unit circle. Now if we are working with an orthogonal matrix, in that case this is a real number, so this is something which has modulus equal to 1, means it is either plus 1 or it is minus 1. So determinant of an orthogonal matrix is either plus 1 or minus 1. And this can be proved quite easily from the fact that if I take A and I take A star, then their determinant is simply related by the result that determinant of this is determinant of A complex conjugate of that. So if I multiply, then I will get determinant of A star A as determinant of this times determinant of this. Because of the complex conjugate, I get determinant A modulus. Now this is identity, so determinant is 1, and hence I get this result. Now this theorem has a geometric interpretation which is not discussed in the book. It is good to know. Suppose I take R2 and I apply some linear transformation with A. As a result, I produce this. That is, I take every point here, apply the linear transformation. If this is A, then I get this point which is AX. So this is a 2 by 2 matrix. Now in that case, the determinant of A has the interpretation of the signed area of these squares. So these are unit squares, say 1, 2, 3, 1, 2, 3. Then this unit square will convert to something. The parallelogram, it is the signed area. So why the sign? Because if this edge comes to this and this edge comes to this, so the orientation has not flipped, then you will just take the usual area. But if you have flipped things, so this edge has come here and this edge has gone there, so this angle has flipped direction, then the sign reverses. It will have a negative area. Now in case of an orthogonal matrix, we know it is either a rotation or a reflection. So if you take this, in that case obviously the area cannot change, so you must have something like this, which is just a rotated version. So this area must be same as that area, or maybe you have reflected it, in which case the sign will be opposite. That is why for an orthogonal matrix the determinant is either 1 or plus 1. However, this intuition works only for R2 to R2, because in R3 you can have multiple flips. So you can have reflection in one direction, then reflection in another direction. The two things together may not give you a rotation, but still the determinant will be 1. But for 2 by 2, its sign is equal to 1, so the determinant is 1 means it's rotation, and minus 1 means it is reflection. For higher dimension, it may be that it's actually composition of multiple reflections. As a result, it still has determinant plus 1. Theorem 7.6.6 is a very important theorem, but stated in a typical Rao Bhim Shankaramish way, in a very bloated way. So this is the main thing. Suppose I have a linear transformation, x being mapped to A times x, then this will preserve inner product if and only if A is unitary. The proof is pretty straightforward. First we do this implication. I take any two x and y and see what is the effect of multiplying them by A from the left. So I get AX and AY. I look at their inner product. Now I am assuming that A is unitary. I am going to show that this inner product is same as inner product between x and y. So this is same as that. I am of course working with our canonical inner product. This theorem is about canonical inner product. Now this thing I can expand because star will kind of distribute with order reversal. So I get this. Now you have A star A. This product is equal to the identity matrix because it is unitary. So I am having y star x, and that is exactly inner product of x and y. For the opposite implication, we have to start with this condition. Whatever xy you give me, the inner product between xy before I have applied the linear transformation is same as the inner product after I have applied the linear transformation, and from this we have to conclude that A must be a unitary matrix. Now this thing can be written as, and similarly this may be written as y star x. I just made a mistake, so it should be y star A star AX. Now these things are equal for all x and y. So in place of x you can put things like EI, the canonical basis. In place of y, you can put EJ. In that case, you will be basically getting the ijth or the jith entry. You will get the jith entry of A star I, and similarly, you will get the jith entry of the identity matrix. So this will basically say that the jith entry of this matrix equals jith entry of that matrix, which will force the entire matrix to be equal to that. In other words, I will have A star A equal to I. Now, do not think that we are cancelling off y here and x there. That is not the reason. The reason is we can put various basis vectors in place of x and y. Now, the theorem can be strengthened. If I have preservation of inner product, naturally it must also preserve norm. So, there is nothing very special about this implication. A unitary implies it preserves inner products. And since norms are defined in terms of inner products, we are talking about Euclidean norm here, so, or the canonical norm. So this implication remains just valid. However, now for this implication, the assumption becomes weaker. I have not assumed for all x and y their inner product is same, but for all x, inner product between x and x remains unchanged by this linear transformation. Even with this weaker assumption, this conclusion remains valid. So I am not showing this implication, I am only proving that implication. So following the argument that I just now showed for inner product, we come to this. So I take any x, consider its norm square, which is x transpose x. I have just put an I there. And also the norm of ax, norm square of ax, which is inner product of ax with itself. So x star s star ax. In the last case, we had got a y star here and x here, y star and x here. So I could put here EI and there EJ or EJ or EI and could say that the ijth elements match. But in this case, I am forced to put EI in both places. Now with this, I can easily show that the ith diagonal entry here must be same as ith diagonal entry there, but that's not enough. Now what I am going to do is, that's the trick, I will be using not EI but EI plus EJ here, similarly EI plus EJ whole star here, and based on that I will get something here equals something there. Now the something that I will be getting, you can check for yourself, will be this. I will be getting A star A, various entries of that. I will get this if I put in place of x EI plus EJ. And similarly, I will get the same thing over here. That same thing is pretty obvious because I will have the same thing with identity here. So the ith diagonal entry of identity is 1, another 1, and this is 0. if I have I not equal to j. My aim is to show that the ijth entry is actually 0. So this will be equal to here 1 plus 1 plus 2 times 0. Now I have already shown by taking x equal to just ei that the diagonal entries match. So this is equal to 1, this is equal to 1. So this must be equal to 0, which means this must be equal to 0, and hence the result. Now the fact that I could write this 2 comes from the reason that this is a symmetric matrix. So if I have a symmetric matrix such that two symmetric matrices such that this holds, then I can basically concluding that the two symmetric matrices must be the same. Now let us see something that we have already discussed, but slightly from a slightly different viewpoint. Suppose we are working over the real field, so our vector spaces are Rn. Now we know that if I have an orthogonal transform on Rn to Rn, in that case that is a linear transform, and it also is an isometry, that is it preserves distances because it is like a rotation or a reflection. Now we have also seen that if it is given to be a linear transform, in that case if it is an isometry, it must be orthogonal, which basically means that these two things together imply orthogonal. So the next natural question is, suppose I do not give you the linearity, I only give you just isometry. Can I say that it has to be an orthogonal transform, it has to be a linear transform? And we can easily say that the answer there is not true, not yes, because of the simple reason that we can have a translation. If I take a translation, that will also be an isometry, it cannot change distances, but clearly it is not a linear transformation because in particular 0 is not going to 0. So mere isometry is not enough to guarantee it is linear or orthogonal, but isometry and linear together will guarantee orthogonal. So the natural question is, suppose I tell you only isometry, what is the most general form, or is there any most general form that you can give me? Of course, if it is linear, it is orthogonal, but suppose something is not linear, then what can you get? Well, the answer turns out to be, it is either an orthogonal thing or a translation or combination thereof, nothing more exotic than that. And that is the main statement of theorem 7.6.7. So here I start with any isometry from Rn to Rn. Isometry means if I take any 2 points and I apply f to them, so this possibly comes here and this possibly comes here. So this distance is same as that distance, and this holds for any 2 given points. Then f must be of this form. It must be some rotation and reflection together with some translation. So it has to be of that form. The idea behind the proof is this. We have to first just assume, while we think in sort of an aside, that this result is correct, and from this we have to express A and C in terms of f, and then prove that that A and that C indeed works. For example, if this is really the case, can you isolate C from f? That is pretty easy. You just take x equal to 0, and that will tell you that C must be equal to f of 0. So I will say, let C be equal to f of 0. I define C like this. Now I want to get this A. So what I will do is, I will take various basis vectors e1, e2, etc. Then A times e1 will give me the first column of A, and I will put it there. So I will get as a rough f of e1, that is equal to the first column of A plus C, which I already know is this. So what I will do is, I will take the first column of A as f of e1 minus this. So I will create A in the following way. The first column is created as f of e1 minus f of 0. The second column is created as f of e2 minus f of 0, and I go on and on and on as f of en, the last one, minus f of 0. So I get a matrix here and I get a vector here. Now I want to show that fx is indeed equal to this, and then I want to show that this matrix is an orthogonal matrix. Now you see, we are getting this pattern many times, f of something minus f of 0. So why not give it a name? So I will call it the new function g, which is basically f of x minus f of 0. So it is basically we are taking f and translating everything by f of 0. Clearly, this is also an isometry because f was an isometry, and if you shift everything by a fixed amount, the lengths do not change. So G is again an isometry. It preserves inner products, it preserves lengths, etc. Okay, so now write it as A equal to G of E1, etc., G of En. Now, since G is an isometry, so it preserves lengths and inner products. So I see that E1 to En, they were all unit vectors. So GE1 to GEn, they are also unit vectors. If I take any EI and EJ, I not equal to J, they were mutually perpendicular. So even after applying G, they will remain mutually perpendicular, which means that all the columns of A are actually form an orthonormal basis, which means that A must be orthogonal. So I have shown this. A is orthogonal. Okay, so C is some vector, A is orthogonal. All that remains to be shown is that fx is indeed equal to this plus this. So we are trying to show that fx equal to x plus c for any x, which means that I am trying to show gx is equal to ax for any x, because if I take this on this side, then f minus c is precisely what we have called g. Okay, so I start by expanding this as a times x. Now what is meant by a? I know that the columns of A are precisely the orthonormal basis GE1, GE2, etc. So I have in my mind GE1 GEN, that is my A. So I am trying to express my GX as a linear combination of these things, and I want to know whether the coefficients that I will be getting are precisely the entries of X are or not. Okay, so I start by expanding this with respect to this inner product, with respect to this orthonormal basis, which is pretty easy to do because it is an orthonormal basis. I have this thing. So I am expanding Gx with respect to these basis vectors. I know that the coefficient of this will be given by the dot product between the vector that I am expanding and the particular basis vector that I am considering. Now I know that G is an isometry, so it preserves inner products and norms. So whether I take inner product between Gx and Gei, it is the same as taking the inner product between X and Ei. So I get a lot of simplification. Now what is this quantity? X, an inner product between Ei. So quickly understand that X is like X1 to Xn, and Ei is like 0, 0 everywhere, 1 only in this position. So if you take inner product, then in that case Xi is the only fellow that is going to survive. So this inner product is nothing but the number Xi. And well, that completes the proof, because I have shown that Gx is a linear combination of Gyis, where the coefficients are precisely what we knew they were, Xi's. So this basically says that this is same as A times X, completing the proof. Theorem 7.6.8 is a very typical Rao Bhim Shankaramish way of stating something which is very important, but in a way which no one can easily understand. So the main idea is this. So I will state the theorem in the more intuitive way. So it is like this, that suppose I have got some vector which I call the vector x. Now someone gives me an orthonormal basis of the space, which we have taken R2 here. My aim is to express x in terms of u and v. So understand that when I am saying I am expressing x in terms of u and v, x itself is given to me in the form x1, x2, which means it is given to me in terms of the canonical orthonormal basis, this vector and that vector. I want to take it to a different orthonormal basis, and we all know that the answer is provided in a very simple way, that x is a linear combination of u and v, where the coefficient of u is given by this inner product, coefficient of v is given by that inner product. Now, I know that whenever I want to express anything in terms of an inner product, I can also do it in terms of matrix multiplication. So this xu can be thought of as u prime x, and this may be considered as v prime x. So if I want to consider these two things, these two coefficients, in that case I might consider them as u transpose v transpose, one stacked on top of another as two rows multiplied by x. So that is the ONB matrix. I am constructing a matrix by taking u and v side by side, a 2 by 2 matrix. Then I am taking transpose of that and pre-multiplying x by this. And this is the important thing to remember. Whenever you are given any ONB, you can express any vector in terms of that. In terms of a matrix, think of the ONB as an orthogonal matrix. You want to find out the coefficients of any x. With respect to this, very simple. You just do A transpose x. That's it. So doing A transpose x is same as expressing A as a bunch of coefficients in terms of the orthonormal basis. Now that is exactly what theorem 7.6.8 says. Whenever you have an ONB and you want to express any vector, it is same as multiplying this by an orthogonal matrix. The same thing of course holds for a unitary matrix. Now one problem with Rao Bhim Shankaram's book is that it mixes up important results with completely useless results, and these two things are of that type. This section was full of very useful results. Unfortunately, these last two things are completely useless. They are just mathematical jugglery. So I am skipping them in this video. So anyone can just follow them from the book. But I would say when you are reading it for the first time, just ignore these things. They have very little use.